A couple of videos ago, we've been talking about variables of fundamental types. And fundamental types are just that. They are always there, but they're very basic. If we want to create variables of some more useful types, then this is what this video is going to be about. And I have to start this video with a disclaimer. Teaching is a little bit about lying, because I don't want to give you all the details straight away to not scare anybody off, and some details are just not important at this level of abstraction. But nothing that you see in this lecture is going to be a bad practice. It's going to be the best practice until this point in the course. If you watch further, you will know maybe something that can be done a bit better. And with that caveat, with this disclaimer, let's roll on. And again, I will be using the same symbols as I used before. Feel free to pause the video and check those out. The most important ones that are kind of still new are the version of C++. If I have the upper facing triangle and the version of C++, it means that whatever is this marked with works with this particular version of C++ and up. And if you have the downward facing triangle, then it holds for all the versions until this version of C++, but not including this version of C++. All of the types that we're going to be talking about today are not part of C++ language itself. They are part of STL, or Standard Template Library, or in other words, the C++ standard library. But this library is so connected to C++ that a lot of people kind of consider it to be even, to a degree, part of the language. It's not, but it's very close to this. And by the way, these videos take a lot of time to make, so if you like them, please do like the videos, subscribe to the channel, ring a bell and whatever all the YouTubers say, and leave any comment. The more comments there are under this video, the more exposure it will get, and the more fun it's going to be discussing stuff in C++ in the comment section. Thanks! From now on, we will be talking about different containers of data. And these containers are just a useful way to store data together, which kind of brings us to a more abstract level and allows us to think about more abstract things by, well, packing the data together. And the first thing we will be talking about is the stud pair, or the standard pair, well, container. It's not really a container per se, but I will, for the sake of simplicity, call it a container here. It basically is just that. It's a pair of values of different types. It is a very useful container. It's used a lot in C++, and we will have a lot more use cases for it coming in later. But if you want to just use it for yourself, then you have to include the utility header and then just use the stud pair. So this is a bit of a new notation for us. We haven't seen this thing before. We have this, again, these comparison operators that kind of, let's call them angular brackets here. These angular brackets, they define which types we want to pass into the standard pair. So for example, if I have the stud pair T1, T2, that means that in the first place of the pair there will be the type T1, and in the second place in this pair there will be the type T2. Let's see a couple of examples. So if I want to, say, make a pair of integer and a string, I can type in the stud pair, then open the angular brackets, type int, type string, close them, and then I can provide the values for it. You can initialize these type of variables in the same way as the variables of fundamental types, with either the equality sign or just the curly brackets here. If you are using C++ 17 and above, which we will be using in this course, then you can omit the types explicitly, because the compiler is smart enough to figure those out. So the same example from above would look in a very similar way with just no angular brackets there. But please remember, they are there, it's just that the compiler knows how to figure those out. And this pairs well with the output streams that we've just seen before, so we can print the first and the second value from our pair, and to do that we just use the keywords first and second, which are part of this pair structure. And that's it. That's basically all there is to a pair, and we can move on to something even more interesting. And when I say a bit more interesting, I mean a lot more data packed together. And in this particular case, we will be talking about the actual containers, the things that are called containers in the C++ standard library. And at this particular case, we will be talking about the so-called sequence containers. Sequence means that stuff is just stored as a sequence. And the first one that I want to talk about is the standard array. It's used for any fixed size collection of the data of the same type. So, for example, if you want to store a bunch of integers together and you know which integers you want to store at compile time, so when you write your program, this is perfect for this. To use the standard array, you have to include the array header and then use the std and then these 4 dots and array to indicate that you want to use it. There is a bunch of ways that you can create the array from the data, depending on which compiler you're using. If you're using C++ 17 and the appropriate compiler and up, then you can omit the types just like you could with the pair. So if I want to create an array of integers, I can just provide the values and let the compiler figure out the type and the size of the array. Because it knows that I provided 3 integers here and they are integers, so it will derive that it's an array of int size. That's basically it. But in the more standard notation, you can always provide the types on your own, and if I want to be extra careful, I would then provide the integer and the size into the array itself. And whenever I say size, I mean an unsigned long. That's like the default type that is used for the sizes of all of those containers that we will be covering here today. After you store the elements in the array, you can of course access those elements. And to do that, we will use a little bit of a new notation for us for now. We will be calling a function on an object of that particular type. So for now we have a type std array, say integer 3, that's the whole name of the type. And we have an instance of this type, let's say arr, which is a variable of that type. And on that variable we can call different functions. So we can call the empty function to check if there are no values stored in it at all. We can call the size function to check how many values are stored in our array. And we can index this array from 0 to basically its size -1. And because we have those indices, we can get every element in that array by index. We can either use square brackets for it or a function at. The difference between those is that when you use square brackets, you're basically telling the compiler, hey, I know what I'm doing, there is an element on that location, and I just want to get it as fast as possible. When you're using at, you say, well, compiler, I'm not sure, so please check if there is an element there, if the size is appropriate, and if the size is smaller, then, throw an error at me, but if the size is good enough, then just give me this element. So it's a little bit more safe, but a little bit more slow. Finally, there are 2 access aliases which are kind of useful, the front and the back, and they basically just map to the first and the last element of the array. Here, really beware that you know what you're doing and the array is not empty, because if it is empty, then this is undefined behavior. So if you're trying to get a first element of an empty array, you will get some reference to a certain element, but this element might not be there and it will just be garbage. Also beware when you try to compute the array size -1. Remember, we talked about this already. If you're working with unsigned long numbers, you might get into the underflow situation if the size is actually 0. Feel free to check this out at the link that I leave at the top of the screen. Finally, we can see how it all works in a small example, and we will have more examples also later in this video, where I include the array, I also use the IOStream to print things out, and then basically I create an array of 3 elements, and then I can print the first one and the last one on the screen. If you do not know the size of your array at compile time, so if you don't have all the values that you want to store in that array while you're writing the program, then standard vector is an answer to what you're looking. It's basically a dynamically resized array. So you can create it empty and then add elements to it as you go, or create it of a certain size and then either reduce or increase its size when you see fit. And to use it, you need to provide the vector include. You can create it very similarly to the array. The only difference is that you don't have to provide this the size of it in the angular brackets. So you just have to provide the data that you're passing into it, and you might provide the type if you are not using C++ 17 and above. You can access all the elements of the vector just the way you could from array, with exactly the same functions and exactly the same caveats to, say, the square bracket operator and the add function. And this is more like of a recommendation. Do use vector a lot. I'd say this is one of the most used structures in C++, period. There is no other structure that I use as often as a vector in my normal life. There are situations where it's not appropriate to use, but these are much more advanced, and we will cover them towards the end of the course. So really do think about this as a default container. If you don't know which container or which sequential container to use a vector. There are things that you can do with the vector that you cannot do with an array. You can change its size by adding elements, removing elements, or maybe clearing it altogether. Let's start with clearing. To clear the vector, you basically just call the function clear on it, and afterwards it will be empty. You can add an element to it with one of the two ways. There is the inplaceback function and the pushback function. The inplaceback is the new standard in C++ from C++ 11 on, but the pushback one is historically more used, and actually is now implemented through use of inplaceback. So generally speaking, you can use either of those in most situations, and we will talk a little bit more about the details here when we start talking about the L values, R values, and how data is moved around in C++, but not now. You can also resize the size of the vector with the function resize. So if you provide a new size which is smaller than the current size that you have, then the elements in the end of the vector will be dropped. If you provide the size which is larger than the current size of your vector, then you will basically generate new elements in the end of the vector. And if you don't provide any more information into the resize function, then they will be left uninitialized, but you can also provide a value for them to be initialized. And remember, if you ever access an uninitialized variable, then this is undefined behavior land, and you're going to be in a world of pain. If you want to remove an element from the back of the vector, you can use popback. And remember, if the element is not there, so if the vector is already empty, then you're again in the undefined behavior land. There are more ways to insert and remove stuff from the vector, but we will talk about them sometime later when we get to talk about iterators. So stay tuned for that. Whenever you add elements to the vector, it changes its size. And when its size changes, it might or might not reallocate all its content into a new chunk of memory, which is what takes a lot of time. If we expect to add elements often, we can also expect that it will try to resize itself very often. And to avoid the time penalty that is incurred by this, we can basically do something clever, and we can say to the vector up front that we expect the vector to have enough memory to store this number of elements. And we do that by using the word reserve, or a function reserve, on the vector object that we have. We basically can say, hey, this is the number of elements that I want you to be able to hold, and from this point on, if we push back or place back elements to it, it will not reallocate until we try to push more elements than we promised to. So always do this. It's really a nice optimization. It makes your code run much faster and still leaves you the flexibility of adding and removing elements to and from a vector. So let's look at this small example here. Let's say we have some vector, we initialize it empty, and then we say we expect 100 iterations, and what we do is we then call the reserve with this 100 iterations. So at this point the vector is expected to hold 100 elements, or be able to hold 100 elements without reallocating its internal memory. And then we just push back or place back the appropriate number of word hello into it, which is a useless task, but it shows the purpose, right? And it will not reallocate while we do this. So let's maybe walk through a small example of everything kind of stuck together with the vector, and you can see it on the screen right now. We basically start with some includes, so we include IOStream, we include the string in the vector, headers, and then we use a bunch of usings. If you don't know what this using is, then go ahead and watch the previous video on the topic. where I talk about this. It's a short one too. Right, and after we use all those usings, we can now use cout, endl, string, and vector without using the stud prefix before them. We can create a vector of numbers, say 1 to 3. We can also create a vector of strings, like if we want to have the Jedi names, let's say we start with Yoda and Anakin, let's say we now want to reserve the size, starting from the size that we already have, +1, because we expect one more. It is a bit of a useless optimization here, but it's just to show how to call a reserve function here, and then we push back Obi-Wan into it, and now we can just print some Jedi and maybe the last number from the initial numbers vector that we have. That's basically how you use a vector, and I hope it all now makes sense. Finally, I wanted to talk about strings, and the strings are basically vectors of characters. That's basically it. To use strings or standard strings, you have to include string header, and you can access the contents of those strings just like you do with the vectors and arrays. In addition, you can concatenate a couple of strings with the plus sign, or like a plus operator. And I also urge you to add this to whichever scope you want to initialize your strings in. So I want you to add this string literal suffix. And it's a bit of a mouthful, but you just have to copy it over and that's it. What it allows to do, it allows to add the s suffix to any literal string that you're typing in your program, something like, let's say, hello world, in the parentheses, and then add s to it in the end, and the compiler will know that it's actually a standard string that you want. So it works very similarly to something like f works for creating a floating point number. And let's see an example here. So we have to include the IOStream, we have to include the string, and then in our main function we can do the usings that we want to do. So we use our s suffix or literal suffix for the string, and then we can create a string by providing the hello and then this s suffix. Then we can type something on the screen. Let's say we ask the user to provide a name, and the user then provides the name and we read it with the cin. Finally, we can print hello and this name, and then maybe also output the lengths of the name that was provided by using the size function. So just like we did with the vector. One more notable difference to the vector here is if you try to print a vector, you will have a hard time. The streams on their own, they do not accept a vector to be printed instantly, so we will have to look into for loops or while loops for that, which comes probably in the next video. With strings you don't have this problem. You can just provide a string and it will be just printed on the screen in its full length. And one more thing about strings that is very important to know is how to convert to and from strings. This is very useful in multiple cases, so we can convert any type, or any fundamental type at least, to string by using the stud2string function. Basically, we just provide as input some number to it, and it will be reproduced as a string. And vice versa, if we want to get a number from a string, we can use a plethora of functions like stud, stoy, stod, stuff, and all the other ones. You can see them on the screen right now. Basically, they convert a string into a given number. If you expect a double, you will get a double out. If you expect a float, you will get a float out. I hope you get the gist. There are many flavors, and just feel free to go to the script that I will provide for these slides that you see on the screen now, and just click all the links and read on all those functions for yourself on cppreference.com. And again, let's look at this small example, which happens somewhere in the main. We can start with a number of 42, of course, and we basically can initialize some string with it, and then we can recover back this number by using the function stoy, or like string to integer. And we could even do it if we have this number surrounded by other strings, because the string to integer function will actually ignore all the text which is not a number. And feel free to play with this more. So provide different numbers, maybe negative numbers, maybe floats, doubles, just try to get a feeling of it and play with it on your own. With all that being said, there is a bunch of caveats that I wanted to talk about before I wrap up this video. Technically, std_string is not a sequence container. It's something a bit different, but it behaves so similarly to a sequence container that for now we'll just stick with that. Second is, really be careful when creating containers with strings. The reason is that because of the heritage of C++, it comes from C, and C had a very different perception of what is a string, and standard string just basically wraps that implementation. Whenever you type stuff in quotes, that will be interpreted by the compiler as a kind of a C-style string, unless you tell it with the suffix that it's actually a standard string, which might or might not cause problems for you. So just beware, and whenever you create containers that have to store string, so for example a vector that stores string, probably specify the type explicitly. It's going to save you some time in debugging afterwards. Okay, the next one is related to the standard vector. Remember how I told you that you can always use the curly brackets or the round brackets, and they're kind of equivalent? They mostly are, but not in the case of a vector. So if you want to create a vector with two elements, you would use curly brackets and put these two elements there, but if you now decide to use round brackets, it will call a completely different constructor. So what it will do, it will take the first number, and it will basically say, well, this is the size of my vector. And then it will take the second number and say, I will fill it with this number. And whenever you want to create, say, a vector of integers or even unsigned long integers, it can be quite confusing. So be aware of this. This is just one caveat that I'm aware of. So take care. I'd still recommend using mostly the curly brackets, but if you want to create a vector of a certain size and fill it with some value, you can do it with the round brackets here. Finally, probably do not use standard vector of bool. It basically is it's a bit of a weird class in itself. It's not really a vector, and it basically stores a bunch of booleans as part of one variable, as bits of this one variable, usually an unsigned long. It behaves weirdly, and it probably doesn't do what you expect it to do, so probably don't use it for now, unless you really know what you're doing. Okay, one final thing that I wanted to chat about here is called aggregate initialization. It's a very neat thing that you can do in C++ 17 and up, where basically you can initialize a couple of variables at the same time from a number of variables on the right, which are stored in, say, a pair or an array. To do that, you must use auto, and you can of course use constant reference and whatever else. So for example, if I want to initialize three integers a, b, and c from an array of three numbers, I would type const auto, then square brackets a, b, c, square bracket closed, and then that all is equal to my array. And because the compiler knows that there are three elements in this array, and because it knows that I want three elements in my aggregate initialization, it will basically just map those values to where they should be. And the same holds for the pair. Because the pair holds two values, we can now map them to two variables if we want to. It's not a thing that I use very often on its own, but I do use it a lot in for loops, and we will be talking about for loops soon, and especially with other even more fun containers. One final remark that I wanted to make is that there are more sequential containers that we've just discussed. There is a list, there is a forward list from C++ 11 on, and there is a deck. All of those have their use cases, but I don't remember ever in my life when I needed to use the standard list. The deck does have its use cases. We might be covering it at some point in this course, but if you know the ones that we did talk about in this course, in this video for now, you're gonna be good. That's mostly what you need to know in your normal programming life. And on that, I want to thank you for your attention, and see you in the next one. Bye.